Good afternoon, dear colleagues and guests. Let me declare open the session of the Dissertation Board for the Defense of Thesis by Tupikina, Elena, Yurevna for the degree of Candidate of Physics and Mathematics, Specialty 010405 Optics, on the subject NMR and IR diagnostics of geometry, energy and electronic structure of hydrogen-bonded complexes. Let me announce the meeting open. According to the order of St. Petersburg University, 1st of April 2019, order number 2861/1, myself, Filipov Nikolai Nikolaevich, professor at the Department of Molecular Spectrology of the Faculty of Physics of St. Petersburg University, was appointed chairman of this dissertation board. Let me also introduce my fellow board members. Stanislav Ivanovich Selivanov, Doctor of Chemical Sciences, Associate Professor of Department of Natural Compounds, Institute of Chemistry, St. Petersburg University. Marina Germanovna Shlyapina, Doctor of Physics and Mathematics, Associate Professor, Department of Nuclear Physics at St. Petersburg State University. Sergei Gurievich Yastrebov, Doctor of Physics and Mathematics, leading researcher at the Yoffer Institute of Physics and Technology of the Russian Academy of Sciences. Unfortunately, Professor Limbach Hans Heinrich of the Free University of Berlin could not attend the meeting. First, let me emphasize that according to the federal law of the 23rd of August 1996, number 127, on science and the state scientific and technical policy, St. Petersburg University has the right to award academic degrees independently. The corresponding order on the procedure for awarding the academic degrees at St. Petersburg University, on the basis of which we are holding this session of the board, was issued on the 1st of September 2016, number 6821/1. In accordance with this order, the session of the Dissertation Board is duly constituted if at least 2/3 of the approved members of the board are participating, but not less than 4 persons. Our Dissertation Board consists of 5 members. 4 board members are present. Thus, there is a quorum. Let me outline the procedure of today's session of the Dissertation Board with a total duration of no more than 2 hours. A chairman brief report on the main content of the documents submitted by the candidate and their compliance with the applicable requirements. Answers to possible questions, 5 minutes. Second, brief presentation by the degree applicant outlining the key points of his study, 15 minutes. Questions to the applicant strictly on her report, no more than 5 minutes per question, and answers of the applicant. Speeches of all the reviews were published at the university website. Speeches of all members of the Decision Board, alternatively with reviews with a statement of their positions, questions and suggestions to the applicant. Not more than 10 minutes for each speaker. Answers of the degree applicant to questions and remarks of members of the Dissertation Board. No more than 15 minutes. Open discussion. Speeches of the attendees with a summary of their positions and or with specific questions and suggestions to the dissertation strictly on the topic of the study, not more than 5 minutes per person. To do that, all the speakers are kindly requested to put their names on the registration sheet and introduce themselves in full before speaking. Final answers of the applicant to the questions, no more than 5 minutes. Speech of the scientific supervisor, not more than 3 minutes. a 5-minute discussion before open voting on awarding or not awarding the academic degree to the candidate. For the time of this discussion, board members' broadcasting shall be suspended. Open individual voting. The chairman of the dissertation board shall count the votes and results shall be recorded in the minutes of the meeting. A decision on awarding or not awarding the academic degree to the applicant. Closing remarks of the applicant. No more than 2 minutes. Before starting the official procedure, let me remind you to switch off your mobile phones. Thank you for your understanding. Let me also inform you that our meeting shall be recorded and broadcast online at SPBU website, and speeches shall be simultaneously translated from one language to another. So, I shall now begin the meeting, and our first item is the Chairman's Summary Report. The thesis of Elena Tupikina for the degree of Candidate of Physics and Mathematics in the specialty 010405 Optics on the theme NMR and IR diagnostics of geometry, energy and electronic structure of complexes with hydrogen bonding was accepted for defense by the order of the Scientific Secretary of St. Petersburg University on the 1st of April 2019, order number 2862/1. The Dissertation Board was appointed by the order of the Scientific Secretary of St. Petersburg University, same date and same order number. And I have already introduced its members to you. The candidate has submitted the following documents to the academic secretary: an application to the rector of SPBU, Professor Kropochev, to accept the thesis for review and defense, submitted on the 4th of March 2019. Review from the supervisor, associate professor, Department of Physical Chemistry and Institute of Chemistry, St. Petersburg University, PhD in Physics and Mathematics, Tolstoy Pyotr Mikhailovich. List of 7 publications which set out the main scientific results of the thesis, including 7 articles published in peer-reviewed scientific publications from the list approved by the Ministry of Education and Science of the Russian Federation. Certificate of training and or the period of training of the 4th of March 2019, number 04A30A, issued by St. Petersburg University, that Tupikina Elena, during the period from 1st of August 2015 to the day of which she was trained in the postgraduate course of St. Petersburg State University in the direction of training, and passed 3 candidate exams in history and philosophy of science, physics and mathematics, English language, special discipline, optics, philosophy for satisfactory, others for excellent. Copy of the master's diploma issued by St. Petersburg University on the 26th of June 2015, the master's degree in physics. The thesis in Russian and English, on paper, on the rights of manuscripts, and in electronic form. The thesis is designed in accordance with the requirements of GOST R7.0. The thesis is printed on a photocopier indicating the output data according to GOST R70.04. It should be noted that all the above listed documents comply with Article 12, Section 3, Thesis Presentation and Defense of the procedure for awarding academic degrees at St. Petersburg University. Appendix number 1 to the order. Now let's give the floor to the applicant for brief presentation. The presentation should not exceed 15 minutes. Good afternoon. Thank you, Mr. Chairman, for introducing me and my work. Let me start my presentation. Among many types of non-valent bonds, they take part in many biological processes, and in recent years studies of hydrogen bonds have shown tendency to search for a parameter decoder, the value of which can be used to assess the properties of hydrogen bonds. Such variant suggested by these include, for example, valence and many others. However, determination of quantitative regularities between hydrogen bonding descriptions in geometry and hydrogen bonded complex energy remains an actual problem. Thus, firstly, the purpose of my study was to develop computational methods of spectral diagnostics of hydrogen bonded complexes. Namely, construction of easy-to-use correlation equations that allow estimating the energy and geometry of hydrogen bonds by the value of spectral parameters. Secondly, the purpose of this dissertation work was to create and test on the model objects a new quantum chemical method of visualization of the features of external electronic shells of isolated molecules, as well as their complexes with hydrogen bonding. Predominantly, the work was performed on quantum chemical methods. This is also part of the work performed on the NMR spectrometer. The results of this work have been published in 7 articles, and several more are in progress. The results of the dissertation were also presented in 29 reports and international conferences. As has already been mentioned, one of the main tasks of this work was to build the numerical relations between the spectral parameters as well as the energy and geometry of hydrogen bonding. The methodology of such studies was as follows. At first, a set of model complexes with hydrogen bonding of this type was selected, so that the hydrogen bonding energy in these complexes covered as wide range as possible. Equilibrium geometries and spectral parameters were calculated for the model complexes. Further, the analysis of the received dependencies was carried out, and parameters of the most sensitive to changes of energy and geometry of hydrogen bonding were revealed. For the set of most successful parameters, numerical correlations between spectral parameters and energy geometry of hydrogen bonding were constructed. Thus, for example, hydrogen bombs, ash species were considered in the study of hydrogen bonds of 2 types. The first type includes complexes formed by the FH molecules, a proton donor, and such fluorinated proton molecules as fluorinated alkyls, FH molecules, intergalactonides, and the second type includes complexes formed by fluoride anion as a proton acceptor, and one or more FH molecules as proton donors. Such choice of complexes allowed to cover the wide range of energy for all these including geometries. NMR and IR spectral parameters were calculated for all the model complexes. Valence oscillation frequencies and low frequency oscillations were calculated by the method of local modes. In the left part of this slide presents the dependence of the complexation energy on the change to the frequency of the valence oscillation. It can be seen that the points corresponding to the neutral and anionic complexes form 2 dependencies, each of which can be approximated by a simple power function. The right part of the slide shows the dependence of the change in the frequency of valence oscillation. It can be seen that the points corresponding to the neutral and anionic complexes can be approximated by a simple curve. Thus, knowing the measured or calculated value of changes in the frequency of the valence oscillation, using the equations obtained in this work, it's possible to estimate both the energy and the geometry of the hydrogen bond. The NMR parameters were also very informative in terms of energy and hydrogen bonding geometry assessment. Thus, for example, the left side of the slide shows the dependencies of the complexation energy on the change of the chemical shift of the bridge proton. it can be seen that the points corresponding to neutral and anionic complexes again form two dependencies. Points for neutral complex can be approximated by a linear function passing through the original coordinates. The angular coefficient is equal to for points corresponding to anionic complexes, the line doesn't pass through the original. Thus, however, the test calculations have showed that the complexation energy values less than 20 calories is a deviation from the linear dependencies observed. The equation given in this paper can be seen for complexes with anionic hydrogen bond, F each F, with complexes formation energy. So the such uncertainty can be lead to variations in the values of change of the chemical shift during complexation as a consequence of linear errors in the estimated values of complexation energy. Yet, with practical use of such ratios, the fact that the chemical shift of the free proton donor is not always known. And in case of weak hydrogen bonds, such small variations in the values of change can lead to significant errors. For hydrogen bonds of NHN type, this problem can be solved in the following way. When an aniline molecule is used, one of the protons of NH2 groups, and its chemical shift can be used as an internal standard against which to calculate the value of change in the chemical shift of the bridge proton. In this part of the work, a series of 19 complexes formed by aniline molecules as a proton donor and a various nitrogen-containing proton acceptors, as well as two molecules with intramolecular hydrogen bond containing aniline-like fragment. Such a set of model objects covers a wide range of hydrogen bonding energies, 2 to 21 kilocalories, and does not contain proton transition systems. In addition, for each complex, the complexation energy was estimated using the correlation relations between complexation energy and the properties of the electron necessity. This slide shows the dependence of the complexation energy on the change in the chemical shift of the bridge proton. The points corresponding to the neutral and anionic hydrogen bonds were approximated by the linear function passing through the origin of the coordinates. The angular coefficient is equal to 1.8 kilograms per mole. It's clear that the given numerical value of the angular coefficient is valid only for hydrogen bonds. For other types of hydrogen bonds, the numerical value of this coefficient can be determined from the ratio of the maximum energy of the hydrogen bond of this type to the maximum chemical shift of the hydrogen bond of this type, corresponding to the quasi-symmetric position of the proton. The dependence of the change in the chemical shift of the bridge proton on the atomic distance can be approximated by the parabolic function, and the dependence of the atomic distance can be exponential. For practical use, these equations can be solved with respect to the interatomic distances. Thus, knowing the measured or calculated value of the change of the chemical shift of the bridge proton in the formation, it's possible to estimate both the energy and the geometry of the hydrogen bond. The next part of the work was devoted to the study of the proton transition process in hydrogen bonding complexes of CHX type. The main task was to trace how the geometric and spectral parameters change. Here, the donor of the proton was 3-nitromethane, and acetylpyridine and fluoride anion were chosen as acceptors of the proton. Equilibrium geometries were calculated for all the modal complexes. Quasi-abatic process of proton transition was simulated and spectral parameters were calculated. Here are the results. For example, for D-nitroethane complexes with proton acceptors, the dependence of the coordinate Q2, which represents the total length of the hydrogen bridge, on the coordinate Q1, 1, which represents the displacement of the proton from the hydrogen bond center, has the expected parabolic form with a minimum correspondence to the symmetric position of the proton. The change in the value of the dihedral angle reflects the change in the skeleton of the dinitroethane molecule. The neutral dinitroethane molecule has a tetrahedral geometry. Changes molecule to flat carbanion with sp2 hybridized carbonyl. The chemical shift of the bridge proton passes through a maximum of the quasi-symmetric hydrogen bond. It's interesting to learn about the behavior of the spin-spin interaction constant when weak complexes are formed when the distance of RCH is slightly lengthened. The value of 1 JCH constant is at first slightly increases by 1 or several tens of hertz, and then begins to decrease exponentially to complexes with already transferred proton. The increase of the constant with a small increase of the RCH distance seems counterintuitive. However, a similar effect is observed in the experiment. For example, the right side of the slide shows in dimethyl sulfoxide. It's obvious that proton acceptability of the solvent increases when switching from carbon tetrachloride to the metal cells. This can be in the chemical shift increases and the signal shifts in a weak field. This can be interpreted as follows. As the proton acceptability of the solvent increases, stronger and stronger complexes are formed. However, for stronger complexes, higher values of the spin-spin interaction are observed. Now let's concentrate on studying the major characteristics of electronic structure of the molecules acceptors of proton, defining geometry and energy of hydrogen communication, namely directions of localization of not divided pairs and ways of their visualization. In this part of the work, results of development, approbation on model objects of the new quantum mechanical approach to visualization of features of an external electronic cover of molecules. Molecule ions and their complexes, hydrogen bonds, are presented. The main idea of this approach is to use the 3 helium atom as a numerical probe to study the electron shells of the. It was expected when the 3 helium atom was placed near the areas of unseparated pair localization or near the potential direction of hydrogen bonding, the electronic shell of the 3 helium atom will be perturbed enough to cause noticeable changes in the chemical shift of the helium atom. Various fluorinated molecules, which are donors and acceptors of the protons, as well as hydrogen bonded complexes, were selected as model objects for testing this technique. To validate the obtained results, the comparison with the classical quantum chemical methods and visualization of the external electronic shells features the function of electronic localization and electrostatic potential was carried out. In the course of this work, it turned out that indeed the chemical shift of the helium atom is sensitive to the peculiarities of the external electron shells. The slide shows the isosurface of the electronic potential, the functions of localization of electrons, and helium atom chemical shift, Laplacian for the fluoroacetylene molecule. All 3 provide qualitative similar information. A little behind CF bond, there is a toroidal region in the direction of about 60 degrees to the main axes, indicating the potential direction of unseparated pairs of the fluorine atom. Around the CC bond, there's also an area in the form of a torus, reflecting the peculiarities of the electronic structure of the triple bond. For the function of the collision of electrons and the Laplacian of the chemical shift of the helium atom, a dome-shaped region near the hydrogen atom is observed, indicating the potential direction of hydrogen bonding formation. As it has been said earlier, the method of designing extremely of external electronic shell featured by means of helium has qualitative comparative information compared to classical kind of methods. It also has some advantages. For instance, the Laplacian 3H helium sensitive to the of external electron shells at relatively long distances. The maximum value of Laplacian of the chemical shift of the helium atom correlates with the degree of localization of the unallocated pairs and therefore can be used for quantitative evaluation. Thus, in this paper, in conclusion, we suggested a number of equations to estimate the energy and geometry of hydrogen bonds by the values experimentally measured or calculated spectral buzzer for hydrogen bonds of NHN types formed in the participation of aniline proton. New coefficients were proposed for recalculation of local electronic kinetic and potential energy density values in the critical point, and hydrogen bond is so it was shown that both geometric and spectral parameters vary significantly among the proton transition coordinate. It was also shown that the three-dimensional probing of the outer electron shells at relatively large distances. Thank you for your attention. Does anyone have any questions to the applicant? Any questions? Any questions to the applicant? And no more than 2 minutes for each speaker, please. Please use the microphone. Ilya Shenderov, Regensburg University. Can you please explain how technically you performed CH proton transfer? We did as follows. The inter-atom distance was measured and the geometry of the rest of the complex was calculated. Then we changed this distance slightly. We made it shorter or longer, and that way we obtained HX. Are you satisfied with this, with the answer? More questions, please. Thank you. Then, please take a seat. Reviews submitted to this thesis. We have some. We have reviews by the board members that I have already introduced, and some external reviews from Alexander Yakimenko, Doctor of Chemistry, Deputy Director for Scientific Work, Vitas Bilevicius and Valdas Sablinkas, Doctors of Sciences, Professors of the University of Vilnius, Alexander Filarovsky, Doctor of Science, Professor at the University of Wrocław. All the reviews were submitted on time as required by paragraph 19 of the procedure for awarding academic degrees at St. Petersburg University, Annex 1 to the order, posted on the official website of the university. Now, let's hear the reviews and comments of the applicant. Not more than 50. We have not more than 15 minutes totally. We start with review by Stanislav Ivanovich Selivanov. The thesis of of Elena Tupikina dissertation is a complete study where our author obtained valuable results in the sphere of methodology and convenient and easy to use calculations. This is my positive opinion given I would like to give to this work and its relevance and practical value, which is beyond any doubt. A growing interest to hydrogen bonds because it plays an important role in chemistry, and progress of the gives new opportunities for more accurate and more convenient exploration of the hydrogen bonds. And the results of the purpose of this work is described as developing new methodology for the study of hydrogen bonds on the basis of results helium shift and approbation of the approach has been achieved. Practical value of the work is not only in identifying various correlations of hydrogen bonds, but in the opportunity to spread these results to other types of hydrogen bonds. The results are especially valuable, especially at least these results are particularly valuable. There are limitations to this. So the advantages of Elena Tupikina's work have been outlined in my review. I'd like to complement Chapter 1. Which contains brief but comprehensive review of the current understanding of the energy of hydrogen bombs, the existing method of describing its geometry. And let me continue to my comments and ask the applicant two questions. I have the following comments to the structure. First, it's not clear why only the first chapter uses the full digitization of its subdivisions. The absence of a similar numbering system in the second and third chapters make it difficult to quickly find the right part of the text. Secondly, the introduction of Russian abbreviations, which have well-known English language analogues, can hardly be considered successful. These are used inconsistently together with their English versions, which have no explanation in the Russian text. Apparently, it would be more convenient and easier to use English abbreviations in the Russian text of the thesis, and in the appendix to give a glossary of the English terms and noun abbreviations, which are not always correct when pronounced in Russian. Translation of the individual parts of the text from English into Russian is not always correct, which leads to distortion of its meaning. A typical example, page 76, the observed shift of the signal of the bridge proton leads to the strengthening of hydrogen bond by 2.5 kilocalories per mole, while in the English version on page 2 says would mean rather than lead to, which is means rather than leads. A total number of technical and spelling errors found in the text does not exceed the average statistical levels in natural science dissertations. In addition to above remarks to the author, I have two questions related to the calculation procedure, interpretation of the results. First, why in Chapter 3, for the conversion of the local electronic, kinetic and potential energy, different coefficients for charge and no charge complexes are given? figures 315, 316, pages 87 and 88 respectively, and the ratios 33, 36, and to recalculate the change in the chemical shift into the hydrogen bonding energy, it is proposed to use a single coefficient for charge and non-charge complexes. And see, my second question is when interpreting the changes in the line width of the 13C and 49 nuclei in the corresponding NMR spectra in different solvents, see figure 3.39 on page 1188. It is stated, I'm quoting, that these changes are related to changes in the electric field gradient at the location of the nitrogen atom of nitro groups, which leads to an increase in the rate of quadruple relaxation during the transition from CCU to DMSO, and the corresponding slowdown in the relaxation rate is explained by the best averaging of the spin-spin interaction constant. My question: why other possible factors capable of influencing the effective relaxation rates are not taken into account when explaining the observed solvent effects? Such factors may be, for example, changes in the time of correlation of diffusion motion of the molecule in the composition of such different complexes, as well as changes in the relative proportion of their existence in the solution. Besides, it's impossible to exclude the contribution of the scalar mechanism of the second order to the relaxation nuclei due to the quadruple relaxation, as well as the influence of dynamic effects on the line width in the recorded spectra. All the above remarks related to the thesis design and the questions that aroused during this reading do not affect the overall positive impression of the work done by the author, and do not raise doubts about the reliability of the conclusions made on this basis, which represent an undoubted theoretical and practical contribution to the methodology of research of the electronic structure of hydrogen-bonded complexes. The thesis of Elena Tupikina on the theme NMR and IR diagnosis, geometry, energy, and electronic structure of hydrogen-bonded complexes meets the requirements established by the order, the 1st of September 2016, order number 681211 on the order of awarding degrees at St. Petersburg University, and applicant Elena Tupikina deserves to be awarded the degree of Candidate of Physics and Mathematics in the specialty 010405 Optics. Clause 11 of the above-mentioned order has not been violated. That's it. Thank you, Dr. Selivanov, for your review and your comments, which I should take into consideration. Let me answer your questions. Your first question about using one function for neutral anion complexes when creating the correlation between the difference of. My answer is that, of course, the energy value depends on the charge, and in some cases this difference can be great, as where we used one approximation function was practically impossible because the error will be too big. In case of NHN bonds, the use of single approximation function makes a model easier and doesn't make the errors deviations greater. The deviation is about 2 kilocalories per mole. This is my answer. Your second question about changes in the line width in different solvents. My thesis contains a supposition about different factors that may affect this change, the change of gradient, and the changes of beta approximation. But in reality, this supposition still has to be tested, experimentally, but the data that we currently have make us believe that gradient of electric field changes. This is my answer. That's it. Are you satisfied, Dr. Selivanov? Thank you for your answers. I agree with the first answer. A second answer, I can accept the relaxation mechanism in general, but the description in your thesis is too straightforward without convincing evidence, and that's why I got this question. The line width is usually much bigger, several tenths of hertz, and so that's how I got this question. So okay, I will do this in the future. Thank you. Now I'll give the floor to Marina Shlyapina. Let me read my review. The study of nonvalent interactions in molecules and crystals is an actual task, in spite of the fact that in comparison with other types of interaction, nonvalent interactions such as hydrogen bonds and van der Waals interactions are weak. They have a significant impact on the structure of molecules and solids as a consequence of their properties. One of the approaches to the study of systems of nonvalent interaction is the search of structural descriptors that characterize the chemical and geometric properties of the molecules, as well as hydrogen bonding parameters. To describe hydrogen bonds as descriptors, both experimental and theoretical parameters, electrostatic potential, frequency of proton valence oscillations, spin-spin interaction, constants, etc., are used. In Tupikina's work, the parameters of IR and NMR spectra, which can be measured experimentally and calculated theoretically, were chosen as such parameters. It should be noted that Tupikina's work is aimed at not only at finding irregularities between the hydrogen bond descriptors and the geometry and energy of the hydrogen bonding complex, but also at determining their quantitative characteristics. I'll skip the description of the paper itself, and I'll proceed to the moving to the evaluation of Elena Tupikina's dissertation work in gel. It's possible to note the following advantages. The author has done a great deal of holistic research, a wide range of model systems with different types of hydrogen communication, with different the new correlations are proposed. The author obtained a lot of new results. High theoretical and experimental level of performance guarantees reliability and reliability of the results obtained. Correlation relations achieved by the author for a number of molecules can be extended on a wide class of connections with various sizes of hydrogen connection that testifies to practical importance of the executed research. Listed above allows to state that the work is executed on an actual theme, and numerous results received by the applicant have both scientific and practical value. The text of the thesis is made of competent and makes a positive impression. Especially it's necessary to note high information content of the text satisfies scientific erudition of the author. Nevertheless, as a result of acquaintance with the work, the following questions remark arose. Firstly, the author writes on page 35 that the outer electronic shell of the helium atom is filled in, so it's expected that 3H helium will not significantly disturb the electronic shells of the probed molecules, and further that there are reasons to believe that when the atom is placed near the areas of collision of separated pairs or near the potential direction of hydrogen bonding, the electronic shell of the atom will be perturbed sufficiently. As confirmation of the first assumption, on page 37, the calculated values of interaction energies are given. They study molecules with the atom. However, it would be interesting to show how the presence of helium atom influences or doesn't influence non-special parameters of the probed molecules, which may be more sensitive to such a weak perturbation from the total energy. The author has theoretically shown the potential possibility of using 3H helium as a probe to investigate the space around the molecule under test. It has been shown that the maximum value of Laplaciana of the chemical shift is proportional to the degree of collision of separated pairs in the molecule under test. However, the chemical shift, the number, is determined in the experiment, and it's not quite clear how this correlation ratio can be used in practice. First question, on page 6, it's noted that a method of calculation was chosen in each case individually, depending on the size of the system and the necessary accuracy. Further, pages 37, 63, and 98 describe the calculation methods used to study the different systems, all of which are different. Page 32, the author substantiates the choice between different methods of optimizing geometry, methods of link clusters and Muller per se, and the calculation of spectral parameters, methods of density functional theory. However, the choice of the functionality itself and the basic sets is not quite understandable. Were any assessments made as to the sensitivity of the calculated parameters to the choice of the exchange correlation function basis? Question 4. Figure 314 shows the correlation of computation energy with interatomic distances and not the result of approximation. The question arises, why does half of the points lie on the one side of the approximation function, the rest of the points lie practically on it, if the approximation was performed by the method of least squares? In the correlation equations, the correlation parameters give without error, but the range of points where the parameters is quite large. It would be good to indicate the error of parameter determination. This also applies to other approximation parameters. And the final comment, the text also contains a number of misprints. Diagrams come under the same number. Table 3.1 is in English. A number of variations are not explained in English language articles that are translated into English are not quoted in the original, but in the translation, etc. However, the marked remarks do not change the purely positive assessment of the work. Especially, it's necessary to note huge volume executed calculations, variety and quality of methods used for their processing, and little review of this was the high qualification of the author. Thus, Elena Tupikina's thesis, NMR and IR diagnostic geometry and electronic structure, the complexes with hydrogen bonds, corresponds to the basic requirements established by the order number 6821 on the order of awarding academic degrees in St. Petersburg University, and Elena Tupikina deserves to be awarded a degree of candidate of physics and mathematics specialty 010405 optics. Clause 11 of the mentioned order has not been violated by the applicant. Thank you. Dr. Shlepova, I'll try to keep all your questions in mind. Your first question was about sensitivity of probed molecules and placing a helium atom near them and how spectral parameters change. In our work, we measured sensitivity of probed molecules. For example, for fluoroacetylene molecule shown in my presentation, the shift is about 1/1,000,000th fraction, so it's relatively small. So we made such estimations. Your second question was about the practical application of the correlation. My answer here is that in this paper, Laplacian is more of a extrapolation, and at the moment, we have not planned any practical testing of this supposition, so we are not quite sure how to do this, but the Laplacian of the shift, but the helium atom shift is now can be measured. Third question about the choice of calculation method, and that it is different in every chapter. If we sensitivity assessment was conducted, and each time we took into consideration accuracy requirements. For instance, using helium atom, we used quite a high level of theory, because in the early stages of our work we had to calculate the interaction energy. So we expected it to be relatively small, so we needed greater accuracy, higher accuracy compared to helium part. In the future, the chemical shift can be used. We can use a simpler method and an easier method to reduce time of the study. And in other parts of my thesis, I actually had reasons to choose a particular method, but maybe I didn't state them very clearly. Your next question was about about the atom to atom distance, if I'm not mistaken. Why some points lie on one side and on approximation was done not only with the method of least squares, but we used other experimental data, and a maximum energy, hydrogen energy value, and this value was obtained for another correlation with other numeric values, and this numeric value was obtained during approximation of energy, correlation of energy to the distance. These correlations included more points because was hard to trace a value of hydrogen bond, but possible, and intermolecular transition, and is not possible because a monomer concept has not been determined yet. There are no points corresponding to the intermolecular distance. And there was one more question to error of parameter determination. Yes. And that the distance between points is really big. Let me explain about the distance between the points. The distance is really great. That's because for complexes with inner hydrogen bond is not very good approximation of the length of hydrogen bond is non-linear, and maybe it would be better to use a sum of these distances, and then these points, the error will be low. There will be fewer errors. Accuracy is several hundredth fraction. So did I miss something? And yes, I accept your comments about the wording and the presentation of my thesis. Thank you. Now I'm going to Sergey Yastribov. Hello, dear colleagues. I enjoyed reading this thesis, and I will not say anything else but pleasure. Well, the theme of the thesis is highly relevant, and I have outlined all my positive comments in my review. And now I would like to proceed to questions. Everything is quite well explained, and I don't have any significant comments or questions to the author. But I have a few minor comments. For example, the author uses quantum chemistry methods, which 2 years ago were very expensive because of computer time. How is the situation now? And is it necessary to forget the classical methods, or the classical methods are still relevant today? And now my questions. applicability of property in external electronic shells of helium-3 atoms to molecules besides the considered fluorinated ones is not discussed in the work. I haven't seen this. According to the data presented, the information content of the helium atom chemical shift, the Placiana maps, is undoubtedly obvious, but we would like to understand that the proposed technique is universal, such as the function of electrons localization. I would like to see a comparison of computational costs. So these are my remarks. So these are all my questions. And in spite of this thesis by Elena Tupikina leaves an overall positive impression as a complete piece of research which meets all the applicable requirements to candidates' thesis, and it NMR and IR diagnostics of geometry, energy, and electronic structure of hydrogen bonded complexes corresponds to the basic requirements established by the order of 1st of September 2016, order number 6821/1, on the order of awarding academic degrees in St. Petersburg University. And applicant Elena Tupikina deserves being awarded a academic degree of candidate of physics and mathematics. Specialty 010405 optics. Clause 11 of the above mentioned order has not been violated by the applicant. Thank you for your attention. Thank you, Dr. Yastribov, about the computational requirements and comparing this to the commonly used methods. Of course, at the moment, this is a big-scale task which requires much more time compared to the other methods, yet today we are working on the possibility to reduce requirements and to reduce computation time, and I think we can reduce this time. And your second question about the if the technique is universal, we're also working to develop this methodology further and make it applicable to classical methods, and the results that we already have, they look very promising, and it shows that this methodology is used for other compounds as well. Thank you very much. I'm satisfied with the answers. Thank you. The next review by a member of the Heinz-Heinrich Limbach, who unfortunately could not attend the meeting. I will read it in Russian. The thesis is devoted to the study of how different properties of hydrogen-bonded complexes depend on each other. In particular, the aim is to search for correlations between spectroscopic parameters, geometries, and energies of the hydrogen bonds. The relevance of these studies arises from the significant role of hydrogen bonds in the stabilization of molecular structures, on chemical reaction, including proton transfers, on crystal packings, on biological processes. Hydrogen bond correlations are useful because it's very difficult. The 100 bond geometries is therefore especially very often appear to be the main source of information, source of energy about hydrogen bonded complexes in condensed state is also quite complicated. Therefore, the spectral parameters often appear to be the main source of information about hydrogen bonded complexes. Then the review contains a review of the thesis, and the author comments on its relevance, and I will just read the closing part of the review. The results of this thesis were presented at several international conferences and published in 5 papers, where Elena Tupikina is the main author. As was mentioned before, the thesis meets the requirements necessary to be awarded degree, specialty 010405, the candidate of physical mathematical sciences. No comments in this review. And finally, a review by the chairman. I will not dwell on the contents of the thesis. I'll just read the conclusions. In general, the dissertation leaves a positive impression. A significant amount of work has been done, a number of new and interesting results have been obtained, and a high level of calculations guarantees their reliability. The text is written in a clear style. Some complaints cause the use of uncommon Russian abbreviations. Also, I have the following questions to the author. Question 1. What are the quantitative estimates of the computational resource intensity of the proposed method of visualization of external electronic shells by means of probing with the help of a helium-3 atom? How realistic are the prospects of its use for complex molecules in comparison with existing classical methods? And the second question. It's assumed that in this paper that the electronic shell of the test atom will not be disturbed enough to cause noticeable changes in the chemical shift of the atom. What are the reasons to consider the electron shell of the molecule under study to be slightly disturbed? And the thesis of Elena Tupikina. In conclusion, I'd like to say that the thesis corresponds to the basic requirements established by the order of 1st of September 2016, 6821/1 on the order of awarding academic degrees at St. Petersburg University. And the applicant, Elena Tupikina, deserves the degree of candidate of physics and mathematics in specialty 010405 optics. Clause 11 of the above-mentioned order has not been violated by the applicant. Thank you for reading the review and your own review. About the your first question about the qualitative estimates of I have already tried to answer this question in part, and well, at the moment it's very time and resource consuming, but we are working to reduce the amount of resources. And well, this the opportunity to use this methodology to in the study of complex molecules will be will come available later. About your second question, if the electron shell is slightly disturbed, we found this by measuring the interaction energy, and this energy remained very small. And as I've already mentioned, the other parameters also seem to be not very sensitive to these changes. The proton chemical shift is also very small. Thank you. I'm quite satisfied with your answers. Now, let me read the external reviews. We have 3 external reviews, and I would like you to answer all the questions of all the 3 reviews. The first review is by Alexander Yakimansky, Doctor of Chemistry, Deputy Head of high molecular compounds, Russian Academy of Sciences. First review of Alexander Yakimansky, Deputy Director for Scientific Work of High Molecular Compounds of the Russian Academy of Sciences. First part contains, outlines the main results and describes relevance of the work, and it also has some comments. The non-linear, strongly non-linear of hydrogen bonding in dinitroethane and pyridine complex presented in figure 3.23b is doubtful, especially when comparing it with the seemingly natural linear geometry of the hydrogen bond in the 3-nitromethane pyridine complex, figure 3.23d. The author B does not give any reasons for such a strong change in the geometry of the hydrogen bond during the transition from a brief mention on page 101 that for dinitroethane and pyridine complex there is an interaction between the pyridine ring and the nitro group of dinitroethane is a statement, not an explanation. It should be emphasized that this remark is made out of debate nature and doesn't reach the high positive assessment of the work. I think that Elena Tupikina's thesis, NMR and IR diagnostics of geometry, energy and electronic structure of hydrogen bound complexes meets the requirements to candidate's thesis, and the author deserves to be awarded the degree of candidate of physics and mathematics, specialty 010405 optics. And the second review by Professors Sablinskas and Bilavichus of Vilnius University. The thesis of Elena Tupikina is dedicated to a quite general topic of application spectroscopy methods in hydrogen bonded systems. Then the review briefly outlines the main statements of the thesis. Elena Tupikina published 7 articles, 4 of them in high-ranking international journals such as Physical Chemistry and C. The decision is based on 4 original publications. One paper recently accepted by Geometry of Chemical Physics. We had several opportunities to get to know the main results of the present research during the 20th, 21st and 22nd International Conferences on Horizons of Hydrogen Bond Research in Belgium, Poland and Finland. Taking into account all formal aspects as well as original results of experiments and advanced theoretical developments, we can state that the present work of Elena Tupikina meets the main requirements of a PhD thesis in Lithuania and many other European countries. We also think that some treatments developed by Elena Tupikina will find applications in related studies in the Faculty of Physics of Vilnius University, and in the future maybe even in joint projects between Vilnius and St. Petersburg universities. And one more review by Alexander Filarovsky. He starts with emphasizing relevance of the thesis, and in conclusion it says it's apparent that for this investigate in detail the physical background, usual growth of spin-spin coupling constant upon slight elongation of the interatomic distance, on the physical nature of such behavior of the spin-spin coupling constant. Thank you very much, Dr. Filipov. Let me comment on Professor Yakimansky's question about nonlinear geometry. This geometry is not sudden. When looking at electrostatic potential of pyridine molecule, it becomes obvious that there's a sphere of high electrostatic potential around the ring, and when forming complexes, it will be drawn to areas with lower potential. And in case of dinitroethane, these are atoms of oxygen. In case of dinitroethane and pyridine, there are two nitrogen groups, so the centers drawn towards these centers, so it is predictably nonlinear. And in case of should be maintain equal distance. So this explains the more linear geometry. So here is my answer. Thank you. So we finished. We're done with reviews, and I know that Gleb Denisov, professor of Department of Molecular Spectroscopy of St. Petersburg University, would like to speak. I will read two reviews addressed to me. These were not officially registered for technical reasons. The first review is by Doctor of Physics and Mathematics, Professor Riltsev, of Inter-Regional Academy of Human Resource Management. The review is positive, and there's one critical note. Among the drawbacks is comparatively rarely used terminology, which does not affect the overall positive impression of the thesis, and the author deserves being awarded a degree. And the second review was submitted by Professor Head of Department of Quantum Chemistry of Russian Chemical Technological University. The review is 4 pages long. It's very classical review, meets all the standard requirements. It's generally positive and has 3 comments which I would like to mention. Density. First comment. As the author says, density of local electronic kinetic potential energy can be measured by X-ray structured methods is not true. For the occasional approximation is used. The use of this method is proved by the article of the author of the review. The second comment. The author mentions the golden standard of modern physics. This golden standard is used when dealing with Schrödinger electronic equation and has nothing to do with calculations in this paper. And then the third comment, only localized basic sets, while the constant screening effects are usually conducted with the flat wave sets. And then the author continues to praise the thesis. The author has conducted enormous work, which is very interesting. The quality of research is very high. Used advanced equipment and software, and the paper meets the thesis meets the requirements meets all the basic requirements set forth by the above-mentioned order, and the applicant deserves being awarded the degree. And in addition, I will maybe add a few words on my own behalf. I would like to express my opinion as the advisor of Elena Tupikina's student project. During that period, Elena Tupikina has been highly motivated and highly interested. Her research has always been systematic and successful. She won several prizes at science and Prospinas conferences. She won prizes. She won scholarship from the government and took part in several important projects. I think she's a highly qualified researcher who can conduct independent research and teaching activities. Thank you for your attention. Would you like to answer any of the comments? Thank you very much, Dr. Denisov, for reading the external reviews and for sharing your opinion. All the comments, they are recommendations, and I'm going to take all these comments into consideration. And the basic sets. Thank you. We shall take all the comments into consideration. Does anyone else want to speak? If no one else, let me give the floor to the scientific supervisor, Pyotr Mikhailovich Tolstoy. Dear board members, dear colleagues, dear friends, I have known Elena Tupikina for a long time, since she was a bachelor student, and during that period of time she became an independent researcher who has mastered a complete set of methods to study the nitrogen bonded complexes. She's very hardworking. You've heard, we've mentioned the articles she has published. She's made over 20 presentations at international conferences. Some of these presentations won prizes and international acclaim, and so the results that she has presented today have been tested at a higher level by famous researchers of hydrogen bonded complexes. So she also won personal grant from a scholarship from the government of St. Petersburg, and she won some national competitions. She won a competition she won the prize to meet with the Nobel Prize winner Landau. 2 times she won grants from DAD for short-term internship in Germany. Elena Tupikina is one of the main researchers involved in 3 grants of Russian Fund of Fundamental Research. She's taken an active part in the work of our laboratory, and she's working with bachelor and master degree students. Despite many a wealth of opportunity, I hope that at least some years Elena Tupikina will stay at the university and continue her work in this at the university. She will hopefully become a leader of a research group. I enjoyed watching a professional and scientific growth of Elena Tupikina, and I hope that our cooperation in spectrology of nonvalent compounds will continue in the future. Thank you, Dr. Tolstoy. Now, members of the board shall need to discuss before the open voting. For this period, please postpone broadcasting and all the attendees who are not members of the board, please leave the room and have a small break. After we finish our discussion, we shall invite you. I'm very pleased to attend this new method of thesis defense, but I must say that sitting here today, and I understood that all the speeches, all the presentations, I was able to understand about 30%. It was very hard to hear. Or maybe the board members should practice more, practice their reading skills. I think that was a big disadvantage of the whole procedure. I approve your thesis. The meeting is resumed. Please turn the sound on and make sure we are on air. It's the most important moment of the meeting. I now put the awarding the academic degree to the open individual voting. Let me remind you that the decision of the Dissertation Board shall be considered positive if more than a half, but not less than 3 members of the Dissertation Board taking part in the meeting vote for it in accordance with Article 23 of the procedure for awarding the academic degrees at St. Petersburg University. Okay, Stanislav Ivanovich Selivanov, your opinion. Thank you. Marina Germanovna Shlyapina, I'm for voting. Sergei Gurievich Yastrebov is a remarkable remarkable paper, and the applicant deserves being awarded the degree. And myself, Professor Nikolai Filippov, is voting for awarding the academic degree. Thus, dear colleagues and guests, let me announce that out of 4 members of the board participating, voted for 4 members, no one voted against, and nobody abstained. The decision on awarding the academic degree of Candidate of Physics and Mathematics, Specialty 010405 Optics to Tupikina Elena has been passed, and we congratulate you. And please, the floor giving the floor to the applicant. I would like to thank all the members of the board for taking their time and finding time to come here. Thank you to my academic advisor, Petr Tolstoy, and Professor Denisov for their clever guidance, for guiding me in my work. Thank you. Big thanks to all the staff of molecular physics department who assisted me, and to my family for their patience. I declare the session closed. Thank you all for your participation. Please stop the online broadcasting.